Okay, everybody. So continuing our discussion of entropy, this is going to be sort of our last proper discussion where we're focused on entropy. Of course, we'll be using it for the rest of the class, and it'll be coming up all the time. So entropy is not going away, but we would like to, in this lecture, finish out studying entropy as a topic itself, okay? And so there's quite a few little things to get through. So it's sort of gonna be little piecewise topics concerning entropy and things related to it. Okay, let's get started. Entropy is a property that a system can have. We've already discussed that. And we know that in any given state, what defines a state is simply a collection of properties. So on any sort of phase diagram or state diagram, there's going to be a point, and that point is going to have, let's say, associated with it, pressure, a specific volume, a temperature, any other property that we might want to measure, and that point is going to have associated with it an entropy, okay? And I'm doing just the intrinsic quantities, so I've done specific entropy, little s. But remember that we have a theorem that says that if we know 2 out of any of those quantities, no matter how long the list is, all we have to know is 2, and they can uniquely tell us all the rest of the properties. So we should have equations that can get any of the rest of these from only 2 of them. And that is what we're going to be heading towards, basically, in this lecture. Now, if we have another point, we had a test question where we know that the path between those 2 points is called a process path. And so the system going between these 2 points, this represents the system, say, at an earlier time, and then at some later time it ends up here. And all in between, it's undergoing a process. And we have different names for those processes depending on certain things that are held constant. So sometimes we had that temperature was held constant, and we called that isothermal. If we had pressure held constant, we called it isobaric. If we had volume held constant, it was isochoric. So you can imagine where I'm going. If entropy is constant, that process is called isentropic. Basically, all we're saying is that if there's S1 and S2, 2 different entropies, then with an isotropic process, S1 equals S2, meaning that the system has changed something. It's gone from one place to the other, so some things are changing, but the entropy is not changing. We can hold that fixed as we change other things around it. That's the definition of isentropic. And you'll remember, I'll throw this up here, that the formula for entropy minus delta S was delta Q over T. And then in the lecture that was just recently before this, when we broke out all the different terms here, we realized that this is really just a formula for the entropy along the normal process that is perfect, or otherwise called the reversible entropy. And then there could be another term, it would actually be in this, somewhere in here, that would be the generated entropy. Okay, so this formula is just for the entropy of the perfect part of the process, or the reversible. Okay, but notice that entropy is linked with heat. That's something we've noticed before. So we've also talked about processes that are adiabatic. I won't write that up, but adiabatic means that we have no heat exchanged, right? Remember that heat is a word for the flow of energy. So technically we're saying adiabatic means no energy was exchanged in the form of heat. No energy moved via heat flow. And so we would expect there to be a link between isentropic, which means this didn't change, or this is 0, and adiabatic, which means this is 0. And there is, but it's not as simple as we might think, because adiabatic and isentropic do not mean exactly the same thing. They're related, though. And here's how they're related. We have the term reversible adiabatic. And this means that there's no, I better get this right, okay. There's no reversible entropy and there's no entropy generated. So, and then of course, adiabatic means that there's no heat. So with reversible adiabatic, think of this as like the most pure process that could ever take place. There's certainly no entropy generated. That means we had a perfect process where if we went in a cycle there and back, we would get the same amount. So no generated entropy at all. It's completely reversible. Not only that, but that process, however we do it, we can do it in a way that there's not even reversible entropy generated. Even the kind that if we just went the other way, we could get it back, even that kind of entropy we're not generating. This is literally no entropy generation of any kind. So it's like the most pure form of a process, reversible adiabatic. Then we have the word isentropic. Now isentropic, we've defined up here, it means that once we get to the next point, like we go from one point to the next, then the total entropy at those 2 points are equal. But what we could have is that entropy generation may offset reversible entropy. And still here, there's no heat. So what this is saying is that the total entropy doesn't change. The total from one state to another, they balance each other out. Well, what might happen is that there's entropy being generated, the irreversible kind, and the reversible, just from the process flowing in that direction, there might be some reversible entropy generated, and those two balance, so that the total difference is 0, right? Like one's positive, one's negative, something like that. So that's isentropic. It's, as you can see, it's not as pure of a process as reversible adiabatic. But it's still pretty good, because the whole thing, start to finish, no entropy change, okay? And then we have just plain old adiabatic, not reversible. And this means with adiabatic, there may be a net entropy change, but still there's no heat. Okay? So all three of these, you'll notice all three of them have no heat. So I guess I could put a fourth one down here, which is like just a crappy process, right? It's got heat. So all of them are sort of good because there's no heat in the process. So they're in some form, in some ways, this is still an idealized process, any of them, because no heat's generated. However, as we go this way, it gets better and better. Here, we're not saying anything about the entropy. All we're saying is there's no heat generated, but the entropy could come from other forms, like mass flow or irreversibilities, okay? Here we're saying that whatever is generated has to be balanced, so maybe there's some being created and flowing out of the system via mass flow or heat or something, but whatever is happening, it's going to balance each other out. And here we're saying absolutely nothing at all, no entropy. And so These are sort of in a hierarchy of implication, meaning that if something is reversible adiabatic, then it's also isentropic and it's also adiabatic. And if something is isentropic, then it's adiabatic. So these things imply those things, but it doesn't work the other way. So adiabatic does not imply isentropic. So that's an important point, that this chain of assumptions only gets to go one way. And so basically, like I said, these are like different processes that we like, but some of them are a little bit better than others, right? So that's like 3 stars, 2 stars, 1 star. All of them are nice processes we like to study, but that one's way better. Okay. Now, let me give myself some space here. Rope that off. I want to introduce a new term to you very quickly that's tied in with entropy. And here's how I'm going to do it. I'll start with delta U equals Q minus W. All right? And I'll move this over, this W over. So I have delta U plus W equals Q. So notice that this is true in general. This is the first law of thermodynamics. So it's always true. The new quantity I want to introduce is just a rewriting of this equation right here, but in a special case. See, this work right here could be any work. We've talked about spring work. We've talked about gravitational work. If I just lift this marker, I'm doing work on it, okay? And on. I could try to think of more off the top of my head, but basically, work comes in lots of different forms. There's one specific form that we talked about that was P delta V. Okay? Now, if the only thing on this side of the equation is P delta V, then what we're saying is that this is a special case, so it's not always true. And it means only form of work is P delta V. That's what I'm saying. I've written this, but I've not written anything else. There's no plus whatever, plus work from gravity, anything else. Only work is in P delta V. Then, this side of the equation I can call a special name. And I can call it the change of enthalpy. All right? So I'm introducing a new letter, H. And here's how you spell it, enthalpy. I've written it here as a change because this side of the equation is a change. Remember that heat here, like heat and work, why isn't there a delta on those? Well, it's because they're already changes. So these are changes of energy, okay? They're like, this is a form of energy flow. Here, H is like the energy itself. And so delta H is a change in H. Let's define H. We're not going to do it perfectly, but H is like a special portion of the total energy, okay? Without doing derivations from calculus, which is going to be a theme in this lecture, without doing that, this is as specific as I can get. Don't worry about it. This is not going to be a huge concept moving forward. I just want to introduce it to you. But basically, there's all of the energy in the system, and depending on if I want to look at special kinds of energy, I can chop it up in different ways. We kind of saw that in our lecture on different forms of energy. And depending on how I chop it up, there's one specific way that I can segregate it and say, yes, some of the energy I want to look at, and then the rest of the energy I don't care about right now. And that's what enthalpy basically is. It's looking at a specific, just a specific group of energy over here, and then the rest I can ignore. Okay? We can see that, right? It's only work from P delta V. So this is what enthalpy is. It's used a lot in chemistry. And of course, like almost everything else, if we divide enthalpy by mass, we get the lowercase version, which is specific enthalpy. That's the last time we get to do that in this class, I'm pretty sure. Okay, but we've done that like, I don't know, half a dozen times already. So, big uppercase version divided by mass, we get the lowercase h, we call it just specific in front of it. Now, there's an interesting note, and that's all we're going to talk about enthalpy. Okay? Yeah, I have nothing more to say about enthalpy. So you can relax, there's not a huge bunch to memorize. However, I do want to make a little note right here. Now that we've seen enthalpy and entropy, the tables in the back of the book are fully understandable. So if you've got your book and you want to go look at the tables in the back, you'll notice that there's a bunch of columns, and in the columns first we've got specific volume, and then we've got, I believe, I had it written down. So yeah, specific internal energy. Then we have, the next one is specific enthalpy, which is what we just learned about. And then the last one is specific entropy. So now, when you flip to the back of your books, you don't have to only pay attention to the first column. You can look at any of them because you know what these mean. Okay? Well, you kind of know what enthalpy means. All right? But, let me close that bracket. But that's just a nice note that we're able to fully understand all those columns in those tables. Okay. Now, a note on those tables is, I'll talk as I'm raising the board. Basically, if you remember what those tables are, they are lab measured values for relating properties to each other. So I started us off at the top of the lecture with the reminder that two properties will uniquely determine every other property in a state. And that's what the tables in the back of the book do. Remember, they define those surfaces. So if you know these 2 points, you can always get this point. Well, we did the surface in 3 dimensions, and that's as much as our brain can visualize. But it turns out that the surfaces have as many dimensions as you want to put independent variables on them. So you could add a 4th dimension and have it be a PVTS surface, and have a whole dimension that had the S information there. Or you could have it be 5-dimensional, have it be a PVTSH surface, and add enthalpy in there. Okay, so really quick, we're not able to visualize this in any way. They're in dimensions we can't understand, but the tables keep track of all the information. Now, we should be able to get formulas, right? So, reversible entropy formulas. So what I'm talking about here are actual mathematical equations. If I can get any of the other variables from just 2, then I should be able to come up with an equation where I plug in 2 variables, and what I get out is everything else I want to know. I can have equations for everything else I want to know. And that is absolutely true. However, in the real world, those equations are crazy impractical. Okay? Almost all of them involve calculus. The ones I'm going to show you today involve calculus. Okay? That's why I'm not going to derive them. I'm just going to put them up. So you can't get very far without getting into very advanced mathematics, solving differential equations, and most of them exist. We're sure they exist. We're guaranteed by a theorem, but we've never solved them just because they're so hard. So it's true, those formulas all exist, but they're totally impractical. What do I mean by reversible entropy? Well, that just means the entropy generated, that comes from randomness in the universe. Things like friction and drag and stuff, that's an irreversibility or an imperfection in the system, that can't really be modeled with equations. So that's just like the oddball, the entropy generated, that's the odd man out. The equations are going to be for the reversible portion, or the portion that if we go backwards, we can nicely get that entropy back. Okay? So let me give you some of just the really simple ones, the ones we can write down. And again, these ones come from calculus, so I'm just going to write the answers for you. So for solids and liquids, we have the delta S equals MC delta T. All right. So, yeah, did I do this right? No, I didn't. I'm thinking of the formula for Q. I'm sorry, this is a log. T2 over T1. That looks better. MC times the log. That's the whole formula. All right? Now, the reason solids and liquids, this is the answer for both of them, by the way, whether it's a solid or a liquid, that's how you do it. The reason why those two are clumped together and they don't include gas is because of the fact that these are considered incompressible. So that means that if we were to put a solid or liquid in a piston, we would just squeeze that down to a certain volume and we couldn't squeeze anymore. We can't just keep squeezing. At some point, you can't compress it anymore. Gases are different. Gases are compressible, and there's all sorts of ramifications to that. We can get work out of that and stuff, and the work doesn't generate entropy, but it's in the formula because calculus reasons, okay? So it's different. It's got to be done differently. This is why we introduced enthalpy. I saved a little bit of room on this board. All right. Notice, here we have Q in the general case. That's always true. And here we have delta H in the special case. We're used to this formula, that Q equals MC delta T. In fact, that's the one I mistakenly wrote just a few seconds ago, okay? And we have been dealing with this thing here, C, which is the specific heat. And we showed multiple times where that came from, how we got that. Specific heat, C. I'll even remind you of that. So, specific heat. That's what C is. And we've been treating it as one single number. Like, it's obviously different for every substance. So water has one, refrigerant 134 has one, mercury would have one, every liquid that we've used, and solids too, like cast iron, molasses, this wood, fake wood tabletop, every solid is going to have a C value that's different. But for every solid, like for water, there's one number. Or is there? It turns out that the reason there was one number is because we were dealing with incompressible substances. We just talked about what incompressible means. For compressible substances, we have a different thing we have to do. We have to say that this is C, I want to get this right, almost did it backwards, CV. This means constant volume. That's what the little v means. So it's specific heat, C, at constant volume, CV. And the reason why we've been using this value of C, which is actually CV, is because for incompressible substances, those substances weren't changing volume. All right, so like the water itself wasn't changing its volume like a gas does. A gas expands, and the same amount of stuff can be wildly different volumes, where solids and liquids are just staying. But if we're dealing with a system that happens to not be at constant volume, like a gas, where we're changing the volume, but we're keeping the pressure constant, we have this, which is the constant pressure. Now, obviously, what I'm about to put here isn't Q, because this number is distinctly different from that number. Remember, that's a feature of now introducing gases. And I should say this right now actually, for water, these two numbers are almost the same. That's why we use the constant volume. If we use the constant pressure version, it's not hardly any different. And so that's why, like, if you looked it up on the internet for liquid water, they're only going to give you one number. It's because Cp and Cv are almost identical. Now let's talk about air. If we are dealing with air, Cv is a very different number than Cp. That means that if this is Q, this can't be Q. So what does this equal? It's not Q. It's delta H, the change of enthalpy. Okay? So constant volume here, constant pressure here. That's the story with gases. We have two different constants. An interesting note, just a side note here, that Cp minus Cv, if you take the difference between them, this is really surprising if you don't know where all this stuff comes from. This is actually R, not the universal one, just the one for each individual substance. So for air, Cp of air minus Cv of air equals the gas constant R for air. So there's an interesting little connection there between things that we already know about. So, two different C's, a Cv and a Cp, mean two different equations. That's why for gas, I'm going to write two different equations here. Delta S, and up here, it's equal to MCV times the natural log of T2 over T1 plus R times the natural log of V2 over V1. And this is, since the volume is changing, right, V2 and V1, at constant pressure. So don't let this throw you. We're using the constant volume coefficient, but it's a constant pressure because this volume is changing. And then it's also equal to MCP ln, same term here. This time though it's minus R ln, and in here these are going to be a pressure difference. And this equation is true at constant volume because we have two different pressures, so what's changing is the pressure. All right. So these are just, I'll reiterate, in theory, we can get much more complicated equations out of here. And I should also mention this is only ideal gases. That's important too. These equations, as complicated as you may think they are, they're only for ideal. If you start using other gas laws to try to drive them, they just get more and more complicated. And same with the solid and liquid. That's the simplest you can write down. It's not crazy accurate. To actually do it, it's crazy, okay? But these are just a few of the simple formulas. We use them on like homework and maybe on the exam or something. The last little note I want to make is going back to the equation that we had. First law of thermodynamics again. Gotta love it always. Delta U equals Q minus W. It's at the top of both boards now. And I would like to write this using what we know about entropy and what we've discussed about the work coming from P delta V. So let me write this like this. Delta U equals T delta S minus P delta V. So for Q, I've just put in T delta S. Remember the delta S is like a conversion factor between Q and T. That's one understatement of it. But I can write Q that way. And then work, of course, P delta V. It's the same work formula that we already talked about up there. And now, here's all I want you to see. This equation has actually got some really deep implications and stuff, but here's what I want you to see. Notice that the properties are paired up. So, for instance, T is multiplied by delta S. So in this term, T and S are paired. And then in this term, P and V, want to end that with a bracket, P and V are paired up. And you're like, what's the big deal on this? Well, I don't really know, without calculus how to show you this, so I'm just going to claim, and you'll have to take my word for it. There's something very deep going on here. There's a lot of mathematics behind this realization that these variables come in pairs with each other, okay? And it turns out that there's different ways of writing this, that there are even more pairs of crazy properties that we're not going to talk about in this class. But there's a very deep sense in which T and S go together and P and V go together. And so for that reason, I want to introduce this concept that we're going to see in, honestly, 2-3 weeks going forward, which is that as we look at processes changing, we're going to plot two graphs. One of them is going to be PV, and I'll write it all intensive properties, so I've got specific volume down there, and TS, that's specific entropy, lowercase s. So we'll look at, as we walk through a process, for example, okay, it goes from here to here, what does that do over here, right? And then we go from here to here, right? And then what does that do over here? Okay, so we'll pair these in terms of graphing them. We'll graph the PV graph, and we'll graph the TS graph. All right, what I would love to do is do a 4-dimensional graph, where I could do PV, T, and S all on one big 4-dimensional thing, but I can't. So I do two separate graphs, one with this pair and one with that pair. All right, so that wraps it up for entropy proper. And then the next discussion, we're going to start on the topic of understanding cycles. All right, thanks guys.